Sorry.
Okay, we'll go ahead and get started. Can the people on Zoom see the slides and hear me okay?
Yep, you sound good.
Thank you. So what I'd like to do today is just kind of go back through chapter 5 and chapter 6 and just review some things in those chapters. Remember, we have an exam on Monday. So we have an exam on Monday that will cover chapters 5 and 6. So as I go through this, if you have any questions, please speak up. But that's the plan for today, is to just do this review. So if you recall, chapter 5 is the thermal chemistry chapter, and that's the chapter that we had a quiz on as well. So hopefully it's somewhat fresh in your mind. So remember, when we talk about thermochemistry, we're talking about energy changes, and usually we're talking about heat. That's the most common. And that leads to a bigger topic called thermodynamics. But for us right now, what we're mostly concerned about is measuring that heat flow, measuring that energy flow. And so one of the things we talked about was potential energy, and with atoms and molecules, you're usually talking about electrostatic potential energy. And so here's the formula for that. Remembering that K is this proportionality constant, 8.99 times 10 to the 9th. And the key thing there is, remember the units, joules, meters per coulomb squared. And the Q values is just the electrical charge. And that's always going to be 1.60 times 10 to the minus 19 coulombs. And one thing that's helpful is to remember the units, usually energy we talk about in joules, but joule is just a shorthand for kilogram meter squared per second squared. So the comment I would make about this, if you get some type of problem where you need to calculate that electrostatic potential energy, or you need to calculate the distance between two atoms or molecules, make sure you remember the units. Hold on a second here. Make sure you remember the units of joule is also equal to kilogram meter squared second squared. Because what that would tell you is, if you set up a problem using this formula, you need to have the distance in meters. That's, to me, the big takeaway there. As you've probably seen with a lot of these, the math isn't real difficult to do. But what's difficult to do is making sure you have your units set up correctly, and then making sure you remember which formula to use. Electrostatic attraction, this was one of our quiz questions from before. Electrostatic attraction is seen between oppositely charged ions. It's the old opposites attract thing that we talked about. And the other thing to remember is that when chemical bonds are formed, energy is released, and energy is consumed when chemical bonds are broken. So in other words, you have to put energy into it to break a chemical bond. When it's formed, energy is given off. We talked about the first law of thermodynamics. And that simply says that energy can be converted from one form to another. But when that happens, you're not creating you're not creating energy, and you're not destroying energy. So the total energy stays the same. You just kind of shift it from one form to another. Once again, that was one of the quiz questions about the first law of thermodynamics. Two terms that we use when we talk about these energy flow type situations is we talk about the system and we talk about the surroundings. So the system is the portion of the universe that we're studying. So a lot of times it's a chemical reaction or something like that that we're studying. The surroundings is just everything else. So in these kind of examples, like we have on the right here, it's that cylinder, it's the container, it's all that stuff. Whereas the system in this case is hydrogen and oxygen molecules, gas molecules that we're doing something with. So a lot of times the questions will talk about the system or the surroundings, you know, is work being done, is heat being generated, things like that. So it's important to remember what that definition of system is and what that definition of surroundings is. We mentioned 3 types of systems. One's an open system, and that's where you can exchange heat and mass. We talked about a closed system. In that case, only heat is exchanged, not mass. And then isolated systems where there's not an exchange of heat or mass with its surroundings. The one that we tend to focus on for most of our work is the closed system, where we're measuring heat exchanging, either coming into or out of things, but the mass is staying the same. We introduced the concept of internal energy, and that's designated by the letter E. And typically we talk about changes in internal energy, so delta E. So once again, that's energy going out of or into the system is what we're talking about. And if we recall, when we talked about that energy flow, we're almost always talking about heat flow. By definition, that change in internal energy, delta E, is the final energy minus the initial energy. So final energy of the system minus the initial energy. If delta E is greater than 0, so in other words, positive, then that tells us the system is absorbing energy. So if it's absorbing energy, is that endothermic or exothermic?
Endothermic.
Endothermic, right. So into is how I think of that. So if energy is absorbed, delta E is going to be positive. Positive means endothermic. And by contrast, if energy is given off by the system, released, then it's going to be negative and it's going to be exothermic. So another thing you should be comfortable with is just that endo-exo thing, which is positive, which is negative. A key thing when we talk about these thermodynamic quantities is that we're used to when we do problems that we report a number and we report units. The units are especially important because they help us with our dimensional analysis. And the dimensional analysis, remember, if we set that up correctly, we really increase our chances of getting the problem correct. But the other thing in these thermodynamic type calculations is the sign is even more important than normally. It's always important, but for these it's even more because of that exothermic, endothermic that we talked about. So exo, remember, by definition is a negative sign, endo is a positive sign. And so this just reinforces it. Positive delta E results when the system gains energy from the surroundings, so an endothermic process. A negative delta E results when the system loses energy to the surroundings, so it's giving off energy, it's exothermic. So a lot of times in some of the calculations you do, you'll have an energy value, certain number of joules or kilojoules, but you'll need to decide, is it endothermic, is it exothermic? Is it giving off that energy or is the energy coming in? And then that'll tell you what sign to apply to that energy value. So once again, thinking about the sign, and this is that energy in, energy out thing, that's really important in these types of calculations. We talked about the relationship of delta E, so that change in internal energy, how that relates to heat and work. And so we said the delta E is equal to Q plus W. Remember, Q is the symbol for heat, and then W is for work. And so these systems can exchange either heat or work. And this table 5.1, if you haven't gotten comfortable with that, you should do that because it says the same thing in general that we've been saying about the exothermic and endothermic. But I think sometimes people get confused a little bit on the work one. So if you are getting confused by that, take a look at this where it says positive means work done on the system and negative means work done by the system. But in general, what you're saying is if it picks up energy or picks up work, the number is going to be positive. If it gives off something, if it gives off heat, if it gives off work, things like that, it's going to be negative. So this is a table I would make sure you're comfortable with, because if you are, then you're probably going to have an easier time identifying whether something is a negative or a positive for the number. We'll say it again just because it is important. Endothermic is plus, that's heat coming into the system, absorbed. And exothermic is negative, that's releasing that heat into the surroundings. We've talked about state functions in the past. We talked about them here a little bit again. Remember, state function is just, you get to a certain point, but you're not that concerned how you got to it, is probably the simplest way to think of it. You know, it's kind of like if you're driving home, there's a bunch of different ways you can get there, but the key thing is you get home and you get to that same place. You're not too concerned about the path. And some of the things that we talk about are state functions, some are not. So you should be familiar with which type of processes are state functions and which are not. So delta E, internal energy, is independent of that path. But the heat and the work, so remember, let's see, we go back here and we said delta E is equal to heat plus work. While delta E is a state function, heat and work, the Q and W, are not. And I think we have an example in a moment here. So once again, internal energy is a state function. It depends only on the state of the system, not how you got there, not the path that the system took to get there. So it depends on that initial and final values for E. Q and W, as I said, are not state functions. And so it does matter how you get to those. For our purposes, usually when we're talking about a change and talking about work, it's usually one of these gas problems. And the work is pushing that piston up it's moving that piston. So for us, this goes back to, while work does factor into some of them, for our purposes, really, we only tend to talk about work when we're talking about different volumes of gas. And remember, we had, in this piston example, we had work was equal to minus P times delta V. So P is that pressure and delta V is just the change in the volume. So on the exam, because all of these are pretty straightforward relations, you won't be given these. You'll have to just either memorize them or look them up, but you will need to know which one is the right one to use. Okay. I'm going to hold off on the homework for a minute here. So I'd like to get through just kind of talking about the things, because you guys can go back and look at the problems when you on your own. And if we have some time at the end, I can go back and look at those. But I mostly want to talk through just some of the meaning of the stuff today. So remember that we introduced something that helps us measure heat flow, and that was the term enthalpy, designated by this letter H. And so enthalpy is the internal energy, which we just finished talking about, plus the product of pressure and volume. When we talk about changes at constant pressure, the change of delta H is the change in energy plus the change in that pressure plus the change in the volume, because the pressure is constant. So if pressure is constant, we can rewrite this as delta H equals delta E plus P delta V. We usually are at constant pressure because we usually are doing things at atmospheric pressure. And so that essentially is constant. If we think back, we said before that delta E is equal to heat plus work. And we previously had said that work is equal to minus P times delta V. So if we go ahead and do some substitution here, what we see is, we see that delta H equals, substituting the Q plus W for delta E, equals Q plus W. And then we see if work is equal to minus P times delta V, we can substitute that in and change the sign to minus work. And it boils down to delta H is equal to Q. So this is what we've been kind of saying, is that when we talk about these energy changes, what we're really talking about is changes in the heat flow. So for constant pressure, that's the key, constant pressure, the change in enthalpy is simply the heat gained or lost. Once again, for delta H, just as with delta E and everything else we've talked about, this endothermic, exothermic approach is the same. So if delta H is positive, it's endothermic. If it's negative, it's exothermic. So no matter which of these things we're talking about, whether they're talking about heat, work, delta E, delta H, this idea of endothermic is a positive number, exothermic is a negative number, that remains the same. So don't get confused on that. And endo means we're putting into it, we're putting energy into it, putting work into it, putting heat into it. And exo is the opposite. Those things are coming out. So remember that linkage. N is the endo, negative is exo, and remember to keep the signs straight on that kind of stuff. Delta H is products minus reactants. So you have the enthalpy of the products minus the enthalpy of the reactants gives us delta H. And we're looking for these differences, these delta H's. In this case, this is the delta H of the reaction. If you recall, there's some other delta H's with different subscripts to them, which denote different processes. But the key is it's in each case, even though they're slightly different what they're looking at, they're talking about the heat flow associated with whatever thing is happening. We talked about something, delta H with the RXN subscript for reaction. So that's the enthalpy of reaction, more commonly just called the heat of the reaction. And that tells us with the reaction, what's going on. Is it exothermic? Is it endothermic? And if so, how much energy is involved? Enthalpy is an extensive property. Does anyone remember what extensive property was? Extensive means it's dependent upon how much stuff you have. So remember when we talked about intensive properties, those are independent of how much stuff you have. And this makes sense. You think about a reaction. Let's talk about an exothermic reaction. If you have a little bit of it and it's an exotherm, well, you're probably not too scared. Think of lighting a match. That'd be an exothermic reaction. But think about if you had, instead of one match, you had a huge pile of something that's explosive, and then an exotherm. You'd have a big explosion. That'd be a bigger problem. So enthalpy is an extensive property. It depends on how much you have. And that's why also think of some of the homework problems you did. There would be like a gram value of how much was involved, or moles, or things like that. And then that energy calculation would come out to be more if you had a bigger amount versus a lesser amount. When we talk about enthalpy of reactions, we'll have a value for delta H written for the reaction written a certain way, certain reactants forming certain products. And there will be a number associated with that, usually in joules, and there will be a sign. The sign, of course, tells us if it's exothermic or endothermic. The size of the number, magnitude of the number, tells us how much energy is involved. Well, if we turn the reaction around and go the other way, the number doesn't change, but the sign does. So remember that. And then the other thing that's important to remember on these type of calculations is, remember we sometimes write in little parentheses a G or an S or an L for solid, liquid, gas designation of that. The physical state of the material matters too. So depending upon the physical state, the delta H value for that reaction will change. We talked a little bit about how, from a practical perspective, how do you do some of these delta H measurements? And that's where the topic of calorimetry came up. And calorimetry is just a way to measure heat flow experimentally. I think, as I mentioned, next semester in a lab, you'll do a lab similar to this, where you basically are measuring the change in the water temperature after you do some type of reaction. We talked about heat capacity and specific heat. So heat capacity, specific heat, and molar heat capacity. Make sure it's clear in your mind the difference between those three terms. So heat capacity is simply the amount of energy needed to raise the temperature of a substance by 1 K or 1 C. Okay, that's the heat capacity. If you're talking about that temperature change for 1 gram of material, then you're talking about the specific heat, which is that C sub S. If you're talking about it with respect to having that 1 degree change per mole, then that's the molar heat capacity, C sub m. So the key thing here is to make sure that you're realizing whether you're working with the specific, the heat capacity itself, or the specific heat, or the molar heat capacity. So these three terms kind of get used interchangeably sometimes, but they are different, okay? So if you're in specific heat where it's on a gram basis, you may be asked to change it to the molar one or vice versa. So make sure you're clear on how to do that and understand that. But make sure you know that the difference between these three terms. And then once again, here's the specific heat equation. So that's the quantity of heat. So that's the Q value over grams of substance times temperature change. So you have heat, usually in joules. It's going to be in joules, mass in grams, and delta T. Once again, since it's a delta T, it doesn't matter if it's in K or in degrees C, because it's a difference. And so sometimes you're asked to do calculations that are based on heat capacity. Down at the bottom is that same formula rearranged. So those two formulas are the same, just rearranged. Top one to solve for specific heat, the bottom one to solve for the heat value. So make sure you're comfortable using this formula to do these types of calculations. Just some more information about the calorimetry experiments. The bomb calorimeter, the thing that was introduced here is that down at the bottom we have the heat for the reaction equals minus C cal times delta T. And C cal is that calorimeter constant. That's something you would determine experimentally for the particular system you're using, and you would plug that number in. But the key thing is that delta T, yeah.
Did you say in a problem we would write the CCal as positive?
Yeah, the way it usually works is they'll give you a CCal, it's almost always positive, and then you plug it in, and then it gets changed to negative in the equation. And the reason why it's usually positive is, you think about it, it should be not participating in the reaction, it shouldn't be doing anything, so it should just be stuff going into it, energy flowing into it. So Hess's law, let's talk about that for a moment. So Hess's law tells us that we can calculate delta H by using these known values of what I would call half reactions, sub-reactions. And this goes back to the fact that this is a state function. It doesn't matter the steps it takes to get there. It's just the beginning and ending heat values. So Hess's law is what tells us by assembling those steps in a way to get us from the beginning to the end of the reaction, we can use those delta H values as long as we're presenting them correctly. And this goes back to that, writing the reaction the correct way, changing the sign if we flip it, and things like that. So whether it's a series of steps, one step, whatever, Hess's law tells us that because delta H is a state function, that we're okay doing that, summing up. So there was some homework associated with that. Let's go on to this. So enthalpy of formation or heat of formation. This is the enthalpy change from the reaction in which a compound is made from its constituent elements in the elemental form. So this is a formation constant, a heat of formation to form a particular compound from kind of its real base starting materials. These are measured under standard conditions. Standard conditions are 25 C, 1 atmosphere, so that's called STP, standard temperature and pressure. And we were just given some values here so you could kind of get a feel for what the range is, pretty big range. But here's the part we want to get to. So if we wanted to calculate delta H for this reaction, so we're taking propane and reacting it with oxygen to form CO2 and H2O. And we know since that's oxygen and then the products are CO2 and H2O that this is a combustion reaction. So we're trying to see if we have information from our delta H table of reactions. Can we kind of piece together a reaction path to get to this from reactants to product? And because of Hess's law, we know if we can do that, then we can just add up those delta H values for the reaction. So if we go and look, we see we have a reaction of propane to graphite and hydrogen. We see that we can take the graphite plus oxygen and form CO2. And we can do hydrogen plus oxygen to form water. If we piece, so there's the individual steps that we're talking about. They're listed. And if we piece them together, we see that, and cancel out the stuff that is cancels, piece it together, we see that we actually get to that final equation. So we can use Hess's law, products, formation of products minus formation reactants. And we just have to remember to use those stoichiometric coefficients. So in this case, those stoichiometric coefficients are the 5 in front of oxygen, 3 in front of CO2, 4 in front of water. So if we go up and we look at the table to see what those formation constants were for each of those compounds, then we would go and we'd be able to fill it in. So remember, we have products minus reactants. So just to remind you, the reason why it's products minus reactants is the values in that table would be formation constants. Okay, so in this case, we're forming CO2, we're forming water, so formation constant is applicable to that. But the propane and the oxygen, and oxygen is kind of a moot point because O2 is always 0 in these things. But for the propane, we're not forming propane, we're degrading it, right? And we said before that when the reaction is written a certain way, and if it's a formation reaction, it would be writing to make some of these things. So if you write it as propane being formed, but now you're saying we don't want it for propane being formed, we want it going the other way, you'd have to change that sign. So by writing the formula this way, products minus reactants, it allows us to change that sign without worrying about it. But that's the reason for that. Okay, we talked about bond enthalpies, so the energy associated with breaking a bond. and we're talking about gaseous substances here. The bond enthalpy is always positive, and that's because we said before that you have to put energy into something to break a bond. We said if we put energy in, that value is going to be positive. The greater that bond enthalpy, the stronger the bond. And then here are just some bond enthalpies here. Once again, to do this, we would add up all the bond enthalpies of the bonds that are broken. And then we would subtract from that the bond enthalpies of the bonds that are formed. Okay. Any questions about any of that stuff? Otherwise, I'm going to go on to chapter 6 and review, just kind of go through some of the theories behind that. And then we can come back and look at some problems if we have some time. Okay, let me pull up. Okay, so chapter 6, we started talking about electronic structure of atoms. A few of you were in lab yesterday and saw some visualization of this stuff. I think you'll like the lab this week because you see visualization of some of this electronic structure stuff that we've been talking about with the orbitals. So, what I'd like to do here is just kind of go through this a little bit again to make sure you're comfortable with what we talked about and some of the relationships. So we talked about the concept of waves, and we talked about how waves pertain to light. And we mentioned that when we're talking about electromagnetic radiation, what we're talking about is light. So no matter what wavelength, doesn't matter, that's just what we're talking about. We also talked about light moves at the speed of light, and there's a constant for that. And it doesn't matter what the wavelength is, it moves at that speed. We introduced the symbol for wavelength down at the bottom there, that kind of upside down Y. And talked about wavelength in the kind of the ocean example is literally from crest to crest. That's the wavelength, it's the length of a wave. A couple of terms we introduced, one was frequency. So wavelength is that distance from peak to peak in the wave. Frequency is how many of the waves you get in a particular time frame. And wave frequency is expressed as either 1/seconds, seconds to the -1, or hertz, which is Hz. So all of those mean the same. So whether the problem says 1/s or s to the -1 or capital H, small z, that's frequency, that's expressing the same thing. We talked about light having a duality of wave and particle properties. And we started to introduce some relationships. So we said the energy of a photon, and the photon we said was this discrete energy packet, and that energy is proportional to 1 over the wavelength. So wavelength, that upside down Y, lambda, the Greek letter lambda, energy is proportional to 1 over lambda. So the bigger the wavelength, so that would mean our denominator gets bigger. So then our energy would get smaller, right? And so remember that energy and wavelength have that inverse relationship. As energy gets bigger, wavelength gets smaller. As wavelength gets bigger, energy gets smaller. It's that inverse relationship. With frequency, that kind of V-looking letter, which is the Greek letter nu, once again, we talked about the unit as 1 over second, or we write it as second to the -1, or here we're talking about hertz, Hz. And what we know is that frequency and wavelength have an inverse relationship also. So frequency equals the speed of light, which is c, and that's expressed in meters per second, divided by the wavelength. So one thing that should jump out at us is if our constant, our speed of light constant is expressed in meters per second, then if we're going to use this formula, our wavelength needs to be in meters. Okay? And that can be a little tricky because most of the time when you talk about wavelengths, you don't say meters. You say nanometers or micrometers or something like that. But to make the equation work for our dimensional analysis, we would have to convert that wavelength into meters because of the units on our speed of light, which are meters per second. If you leave it in nanometers or something like that, it's not going to work out because the units won't cancel properly. So this is another relationship that you should know. Just as this is one you should know, the energy equals 1 over the wavelength, and frequency equals speed of light divided by wavelength. This just reinforces some of this, the electromagnetic spectrum, going from gamma rays, X-rays, UV, Vis, IR, microwaves, radio waves, kind of giving you a feel for the size of the waves, the length of the waves. And then those arrows there, once again, highlight this learnings that we have about frequency and wavelength and energy and wavelength. Here we just talked about what some of these different wavelengths mean. We rearranged down at the bottom here our formula that says the speed of light equals wavelength times frequency. And that makes sense because we said that wavelength units in this formula need to be in meters, and frequency is going to be in 1 over seconds. So if you multiply meters from a units perspective, if you multiply meters times 1 over second, you get meters per second. And that's the units we want for our speed of light. So once again, just kind of reinforcing, if you line your units up, then you have a much better chance of solving the equation correctly. So these prefixes we talked about, I don't remember if it was in chapter 1 or chapter 2, but we talked about them early in the semester. If you have forgotten them, I would suggest going back and looking at table 6.1 here and getting comfortable with things like angstrom. That's the capital A with the little circle over the top. That's 10 to the minus 10th meters. Nanometer, the small nm, is 10 to the minus 9. Micrometer, 10 to the minus 6. Millimeter, 10 to the minus 3rd. Centimeter, 10 to the minus 2. So make sure that you're comfortable with and you remember what those prefixes mean. Because this is what I was saying before, is to use those formulas that we were just talking about. It needs to be in meters. But there's a good chance that the wavelength information you are given is not in meters. Nanometers is pretty common, angstrom is somewhat common, but nanometers, micrometers, those are pretty common. And so if you get one of those, you need to be able to convert it into meters, and this is the guide for doing that. We talked about why the initial theory that light was just waves didn't hold up. And there were the three things that were observed that led them to the dual nature of light. So the wave properties and then the photon packets. And that was the black body radiation, the photoelectric effect, and then emission spectra. Remember, black body radiation is emission of light from hot objects. So in other words, you heat something up and you start to see it glow. Okay, that's that black body radiation. The photoelectric effect was if you have a really clean metal surface and you put light onto it, if it's the right frequency light, you will get emission of electrons. If it's the wrong frequency of light, it doesn't matter how intense the light is, you don't get anything coming off. And then finally, the last one, emission of light from electronically excited gas atoms. That's known as emission spectra. And I think I mentioned there's a whole discipline within analytical chemistry where they use this to do analysis, mostly of metals. So if you ever wonder how they know there's like 10 ppb of iron in your water or something like that, it's usually an emission spectra based technique. So when we talked about the chunks of energy, the packets of energy, the quanta of energy, those were all terms that were used. It led to this formula with Planck's constant in it. And that is energy equals Planck's constant times the frequency. And there's Planck's constant, but the key thing is you look at the units, joules second. Okay, so it's not joules minus second, it's not joules over seconds, it's joules second. And so if you think about that, if that's joule second, and we know frequency, the units of that is going to be 1 over seconds. If we do the dimensional analysis of those units, then the seconds will cancel because we'll have a seconds in the numerator, seconds in the denominator, and we'll be left with joules. That's great. Energy is often expressed in joules, so the units work there. So what this does, though, is it gives us another pretty straightforward relationship, which if we know frequency, we can calculate an energy value. If we have an energy value, we can figure out what frequency that is. We had some other formulas that showed us the relationship between frequency and wavelength. So we could use those if we were given, for instance, a wavelength to start with. We could use one of those relationships to convert that wavelength to a frequency. Remember, that's that inverse proportionality. And then we could then plug it in here and get an energy value. So one of the things that was learned is that matter can only emit or absorb energy in whole number units of that HV, that Planck's constant times the frequency. And so we call this specific energy levels. We say that that means it's quantized. And so I think of it as it's almost like a puzzle piece. It's like it can only fit in if the piece lines up If the piece is too big or too little, then it doesn't fit in. This just gives some information about the photoelectric effect. The big thing that came out of all this is that we call this energy packets. We don't really call them quanta or anything, they call them photons. And those photons, in order to be absorbed or emitted, they must meet whatever that difference in energy level is. If it's too big or too little, if it doesn't fit in, then it's not going to work. And the atomic emission stuff. The thing to remember about the atomic emission is that this is where we talked a little bit about the continuous light spectrum and a line spectrum of light. And so in the room, you look up and you see the lights are on, and that's an example of continuous spectrum of light. So you've got a wide range of wavelengths that light source is emitting, and you kind of see the result of all of them blended together. With a line spectrum, you only see discrete wavelengths, and those discrete wavelengths are representative of a particular element. So each element has its own set of discrete wavelengths that it emits. So it's called its emission spectrum, or this we're calling line spectrum, but emission spectrum. And so by looking at those wavelengths, you can identify what the element is. So we had the Rydberg equation here. And what this is doing is it's giving us a relationship between those different N values with regards to wavelength. And so I think we had some homework problems associated with using this formula, where you went from different level to different level. That's the N values. And then you have a constant there and then a wavelength. So here they talk about, once again, that there are certain energy levels you can go to based on the energy levels for that particular atom. When we talk about the energy levels, we talk about ground states and excited states. And so when the electrons are in their lowest energy level, that's called the ground state. And remember, we'll talk about that with our electron configurations. That's an example of ground state electrons and how they're arranged. If you go to a higher energy state, so in other words, n equals 2 or more, then those are called the excited states. And so to go from that ground state to excited state, that energy difference has to be met exactly with whatever the energy source that you're putting it into is. And then once you go to one of those higher energy states, it can only come down to one of the allowed energy states that are present. And then that photon that's emitted will be of that energy. That's the difference in the energy states. If it's a positive delta E value, a change in energy, that means you absorbed energy. If it's a negative, it means that photon is given off at that energy. So even in these types of transitions, that absorb is a plus, that giving off is a negative. We talked about how this all sounded really good and we were excited about it, thought this is great. but it only worked for hydrogen. And unfortunately, for Bohr, there's a lot more going on than hydrogen. And that's when we started talking about, well, he had some good things. Electrons exist only in discrete energy levels, which you can describe by quantum numbers. And we'll talk about those quantum numbers again in a moment. And that energy is involved in the transition of an electron from one level to another. So those are some good things that came out of his theory, but there were some weaknesses, and that led us back to this dual nature, this wave and photon type nature. And so we got another relationship here. We had wavelength equals Planck's constant divided by mass times velocity. Mass times velocity is known as momentum. So what that tells us is wavelength equals Planck's constant divided by momentum. Then we got to the Heisenberg uncertainty principle. So what Heisenberg demonstrated is that the more precisely you know the momentum, the less you know about its position. So, and this is the uncertainty principle. Schrodinger then took that information and developed some math. And this is the stuff you're going to look at in the lab this week. And so that's where we get these density structures. So that's those wave equations squared tell us the dot density. And this whole idea of these electron densities and all this kind of stuff of predicting where the electrons are at any given time, that's what we call quantum mechanics. And over on the picture there on the right, you see there's a lot of places there where there's dots. So that tells us there's a lot of places that there's a possibility of the electron being. But the more dots there are, the greater the likelihood that's where the electrons are going to be. So these plots are known as electron density plots. And as I said, that's the probability of finding an electron somewhere. And this led us to the concept of orbitals. And orbital is the term we use to say where the electrons are located. And so as we have that description of orbitals through the quantum numbers, that tells us the probability of where the electron could be. And so there's 3 quantum numbers that describe the shape and the size and location and all that stuff. And let's talk about those again. So we had our principal quantum number, which is n, and n are integers of greater than or equal to 1. And this principal quantum number, n, it describes the energy level on which the orbital resides. So n of 1 is the first energy level, n of 2 the second energy level, n of 3 third, and on down the line. As that n number increases, the orbital becomes larger. And because it becomes larger, the electron spends more time farther from the nucleus. The electron has higher energy as that n number increases, and it's less tightly bound to the nucleus. So we'll talk a little bit about 1s and 2s and things like that, but what you'll see visually this week in the lab is as you go to those higher energy levels, that s orbital gets bigger and bigger. And that's what this is saying. The second quantum number we talked about is the angular momentum quantum number, or the small l designation. And this defines the shape of the orbital. And so there are defined values that this quantum number can have based on that principal quantum number. So if principal quantum number is n, then the angular momentum quantum number, which we're calling L, can be integers ranging from 0 to n minus 1. So again, we have examples here in this little table of values of L of 0, 1, 2, and 3. Well, by convention, we don't use the numbers when we're describing the orbitals. We have these letter designations that we're using instead. So we have S, P, D, F, and the S corresponds to an L value of 0, P corresponds to 1, D2, and F3. So when we start writing these things out, we'll have a number, which is that principal quantum number, which is the energy level. And then we'll have a letter, which is this angular momentum quantum number, L. So the first number, 2, for instance, would be the energy level. Then the letter would tell us, well, what's it look like? What's the shape? And that's where the SPDF comes in. Then the third quantum number is something called the magnetic quantum number. And this gives the three-dimensional orientation. So once again, this is something you'll see in the lab this week because it's like these 3D pictures that you can rotate around. So it's good to think of, for instance, in this one, it's good to think of the shape. It's a circle, or it's a lobe-looking thing, or something like that. But it's not a two-dimensional situation. It's a three-dimensional situation. And so this, what the magnetic quantum number does, is it tells us, if you recall, we had that X, Y, and Z coordinate system. It tells us how things are going in the 3 dimensions. So it gives us that third dimension, and that's what this is doing. And so the allowed values for M sub L, that magnetic quantum number, are minus L to positive L, including 0. So we go back here and we say the L values were based on the principal quantum number, N. And so it's n minus 1 tells us which of these. So for instance, if our L value was 2, okay, then this would be minus 2, 1, 0, 1, 2 for the M sub L. So we would have all of those integers there. And sure enough, we look down here and we see that on any given energy level, you can have up to 1 s orbital, 3 p orbitals, 5 d orbitals, 7 f orbitals on down the line. And each of those orbitals can hold 2 electrons. So you can have 6 electrons in the p orbitals, 10 electrons in the d orbitals, 14 electrons in an f orbital, and 2 electrons in an s orbital. We talked about shells, subshells, orbitals, all this stuff. So the shell with the principal quantum number consists of exactly n subshells. And each subshell consists of a number of orbitals. Total number of orbitals in a shell is n squared, where n is that principal quantum number of the shell. So this kind of relationship, just something you're going to want to remember. And this is table 6.2. If you're going to spend some time learning the table, this would be a good one to learn. Because what this does is, it breaks down what our options are based on these quantum numbers. And so what we see here on the left, we see n the principal quantum number. And it tells us, for instance, in the first one, if n is 1, then possible values of L, because remember L is n minus 1, it's just the 0 number, okay? And then that designation is 1s, and the possible values for m sub L, it's 0. Because remember we said s is the 0. And so that tells us we have one orbital in the subshell, and the total number of orbitals in the whole thing is 1, because there's just one subshell for this. If we look at quantum number 2, principal quantum number 2, we see that we can have possible values of L of 1 and 0. So that puts us at 2s and 2p. Because remember, if L is 0, it's S. If L is 1, it's P. And then based on that, the possible values of n sub L, we know there's one of them for S, and so that's the 0. There's 3 for P. That's 1, 0, minus 1. And so from the P subshell, we have 3 orbitals. From the S subshell, we have 1 orbital, and that's a total of 4 orbitals in this quantum number 2 shell. And then you can go on down the line and look at 3 and 4 and continue on as much as you want. But it's that same idea. So I would suggest looking over this table, make sure you understand kind of what the different designations are and how it all fits together. Here we get to some of the electron density presentations or contour model presentations, showing what these orbitals look like. So here's the s orbital. It's pretty much just a circle or a ball, however you want to think of it. But the key thing here is as you go to higher energy levels, as we said, it gets bigger. There's also these radial probability function plots, which tell us what's the probability of finding the electron in terms of distance from the nucleus. And we see as we get to the bigger n values, so higher energy values, that probability starts to increase. You still find it in those lower levels, those lower distances, but it gets more likely to be found as you get further from the nucleus, as the size grows. Okay, p orbitals. Typically, the p orbitals are these lobe-looking things. They call them lobes, kind of like a stretched out balloon with a node in between. The node means there's no likelihood of finding it there. And what you see here also is, and this is what we were talking about, that third quantum number gives us orientation. So in each of these, it looks the same, right? It's just 2 lobes. So that second quantum number, which tells us the shape, is telling us it all looks the same. But that third quantum number, that's the orientation. One of them is along the z-axis. One of them is along the x-axis. One of them is along the y-axis. D orbitals, we see it gets a little more complicated there. We see 4 of them have 4 lobes. And then the 5th one is kind of a weird one in that it's 2 lobes and then the donut looking thing in the middle. F, it says it's very complicated. There's a bunch of F orbital stuff in the lab, so you'll see what they mean by that. It's certainly complicated, but it's actually pretty neat looking. We talked a little bit about the energies of the orbitals using the hydrogen. atom as an example, and we talked about how energy levels, where they're at this same energy, that's called degenerate. And so here we see 1s is kind of a trivial one because there's just the one, but 2s and 2p, those are both at the same energy level. And then we go on from there. What we learned though is that when you get to things that are more complicated, it doesn't hold up. And what you really see is that there are subtle differences between these energy levels. And really the only thing that stays degenerate is the orbitals which is within that sublevel. So in other words, all the 2p's are at the same energy level. All the 3p's all are at the same energy level. All the 3d's are at the same energy level. But what we see is that 1s, we go to 2s, the 2s and 2p are at slightly different energy levels. We get to the 3, n equals 3, and we see 3s and 3p are at different energy levels, 3d's at an even different energy level, and more importantly, now we've got 4s, which we would expect to be at a higher energy level than the 3's, is actually lower, slightly lower than the 3d. So that degenerate notion on the energy levels, it stays there for these sublevels, these 3p, 3d, things like that, but it doesn't hold up in terms of all the 3's being at the same energy level, all the 2's, things like that. The last quantum number we introduced was the spin quantum number, where we said it's either plus a half or minus a half. Where this really comes into play is this helps explain how none of these electrons have exactly the same set of quantum numbers, because you can have the first 3 the same, but then you have a different designation on the spin here. So Pauli exclusion principle, no 2 electrons can have the same set of 4 quantum numbers. And that means no 2 electrons in the same atom can have the exact same energy. And so this means that every electron in an atom must differ by at least one of those 4 quantum numbers. And like I said, that's where the spin really a lot of times is the tiebreaker on that. All the other 3 will be the same, the spin will be the difference. We talked about electron configurations. We said we want to write things in the lowest energy possible. That's called the ground state. And when we write these, we have a number that denotes the energy level. In this case, that's the 4. The letter denotes the type of orbital. In this case, it's P. And then the superscript denotes the number of electrons. In this case, that's the 5. We talked about how when we write these, use the box approach to write these diagrams. We have half arrows designating the spin. We write by convention the arrow going up until we start pairing them. Then the next arrow will be down. So we never write the box so that they both in the box are either up or down. If there's 2 in there, one's got to go up and one's got to go down. We talked about Hund's rule. When we're filling degenerate orbitals, the lowest energy is by having the same spin maximized. So in other words, when we're filling a degenerate set, we want all of the arrows facing up. We don't start pairing them till we fill them all with one facing up. We talked about electron configurations. That really what we're after usually is looking at those valence electrons. And the valence electrons are the ones that are in that outer shell. So the outer shell we define as those AA noble gases. If we look at the electron configuration for those, it's the electrons after that for the element we're interested in. We went through kind of transition metals and the lanthanides and actinides and talked about those a little bit, how to write those. We had this where we kind of talked about how 1A, 2A, those are the s electrons. The transition metals would be the d electrons, and then the ones to the right of the transition metals, those will be the p electrons. I think I said this probably about 10 times last class, but this is a slide that I would get comfortable with. I would make sure you understand this slide where it talks about how these things fill. And so there are exceptions to the rules, but for the most part, this is how they fill. 1A, 2A, 2P, 3S, 3P, 4S, 3D, 4P, on down the line. And then there for selenium is one of the shorthand ways using that, in this case, argon noble gas core, and then the valence electrons would be that 4s2, 3d10, 4p4. There are some exceptions, two prominent ones, you should know these, chromium and copper. And so rather than filling for chromium, for instance, instead of filling 4s2, 3d4, they fill 4s1, 3d5. And then copper fills 4s2, rather 4s1, 3d10 rather than 4s2, 3d9. And that's to preserve those fully half-filled energy levels. And I think that's it. So take a look at some of the homework problems, get comfortable with the math, but I think more importantly, make sure you're comfortable with when to use what formula, how the formulas, what the purpose of the formulas are, what units need to be in the formulas, and things like that. I know everyone gets hung up on the math problems and all that, but if you don't understand what goes into setting up the problem, it's difficult to solve the problem. So unless someone has a question, that's it for today. On Monday, the exam will be posted in Canvas as normal, and then just go ahead and take it, and then we'll go from there. All right, thank you.